we're going to prove that if a sequence of functions converges uniformly to f, and each f sub n is integrable on AB, then f has to be integrable, and the limit of the integrals is equal to the integral of the limit. And the fact that f is integrable has already been done earlier. So we're just going to assume this part. So I'm just going to prove that the limit of the integrals is the integral of the limit. So the idea is, this is just kind of a basic idea from what we saw before. A sub n goes to A if and only if, for all epsilon bigger than 0, there exists a capital N such that n bigger than or equal to n implies A sub n minus A is less than epsilon. Well, remember, these are just numbers, but actually, and I'm just going to suppress the A and the B. I'm going to be really lazy. So integral of f sub n is supposed to be equal to, you're supposed to imagine that there's an A, B, and an A there and a B there, except I'm just not going to write these because I'm lazy. Right? I can just write A sub n is equal to the integral of f sub n, because that's just a number. The integral is just the area of this particular function f sub n between A and B. And similarly, my A is just going to be the integral of f. So really, I need for all n there exists that such that the integral of f sub n minus the integral of f, both assumed to be on AB, is less than epsilon. So that's the way the proof is going to go. So let's actually prove it. So proof. I need to prove for all epsilon, so I'm going to let epsilon be bigger than 0. And then the punchline of the proof is that I'm going to have then for all n bigger than or equal to capital N, we have, it's going to be the integral of f sub, if you subtract the integrals for large enough n, you're going to get something less than epsilon. That's the way the proof is going to go. That's the way these proofs of numbers of sequences of numbers always goes. But first, I'm going to use uniform continuity to help me get the capital N. So, so I've, since f sub n goes to f uniformly, there exists a capital N belonging to the natural numbers, such that for all little n bigger than it, and all x belong to the interval, we have f sub n of x minus f of x is less than epsilon, except I don't want epsilon. I'm going to do epsilon over b minus a. So I can use that. That's uniform convergence. It doesn't matter what x is. This is always going to be true because of uniform convergence. So this would not be true pointwise, but I'm not assuming pointwise. Now, for all little n bigger than or equal to this same capital N, we have this thing is equal to, well, whenever you have the integral, whenever you add or subtract integrals, you can combine them into one big integral. F sub n minus f. That's, you know, from calculus. And then, I'll really make this an integral sign. Maybe I'll start writing a and b here now. We also know that we can, at the cost of an inequality, we can put the absolute value signs inside f sub n minus f, like so. But we've proved already that this, as long as n is sufficiently big, which it is, this is going to be less than or equal to, or it's going to be strictly less than, epsilon over p minus a. Well, epsilon is a constant, so this is just equal to epsilon times b minus a times the length of the interval, which is b minus a. Cancel, cancel, you're just left with equals epsilon. So we get that this thing is less than epsilon, and we've proved the result. So we're done. So I'm going to continue the screencast a little bit longer in the second part, and I'm just going to explain why pointwise will not work. You see where you need uniform, we use uniform continuity here, but why won't pointwise work necessarily? So stay tuned.